Welcome to the class of design of RC structure. In the last class, we have discussed about design of one-way slab, and in the last class we go through for the check for deflection. Okay. Now this problem is incomplete without calculating our development length. So the final step is come as step 8, that is check for development length. Okay. For the checking of development length, I would like to suggest that go through the IS 456 code 2000 and clause number 26.2.1, clause 26.2.1. Go through this clause. We'll completely can study about this development length theorem, and I also sent some PDF file about development length that you can easily learn about this. So what clause 26.2.1 says? It says that our development length LD will be 0.87 Fy into dB divided by 4 tau bt. Okay, so there are few terms that is unknown, like what is Fy? We all know that is ultimate tensile strength. Okay, now this is this dB. Okay, this dB, this is nothing but dia of main bar. In this our problem we use dia of main bar as 10 millimeters. So our dB is fixed, that is 10 millimeters. Now this is a new term, that is tau bt. Okay, actually this is a stress that comes for the bonding. Okay, so this is a bonding stress. So for this tau bt we have to check what values our come. So finally LD is 0.87 into Fy value is 415 into dB. dB means our dia of main bar, that is 10, divided by 4 into tau bt. Okay, now what is tau bt? Tau bt is 1.4. now we multiply a term, that is 1.6. so why 1.6? 1.6 terms comes as in limit state of design 60% bond stress is increased, so 60% increase means we have to multiply 1.6 term for in case of calculating of development length. So if we calculate, the value comes this is 404 millimeters. So this is our development length. Now we have to check. How we can check? Number 1, according to clause 26.2.3.3a, it says that our embedded length into the support should be greater than this LD divided by 3. Okay, so what is step? Embedded or embedment length into the support should be greater than this LD divided by 3. This is according to clause number 26.2.3.31 of IS 456 2000. So for 10 mm dia bar, as we use 10 mm dia as main bar of our one-way slab, So this LD by 3 is equal to 404 divided by 3, so that means 134.3 millimeters. Okay, now we have to calculate what is the our length of bar embedment at support. So let's calculate our embedment length. So length of bar embedment at support is equal to how much? You can clearly see from the geometry, that is the width of the support minus clear cover. So this is width of support minus clear cover. So our width of support is how much? Our width of support is, what was our width of support? This is given in the problem. This is 230. Okay, and clear cover was how much? Clear cover was 30. Okay, so we can write that width of support is 230 minus clear cover is 30, so value comes 200 millimeter. Now this 200 millimeter is obviously greater than this LD by 3, that is 134.3. So I can say this is greater than 134.3, that means LD by 3. Okay, so this is okay. Check. Now we have to check another portion about in terms of moment. Number 2 is at simple support. This is according to clause number 26.2.3.3d. It says that our LD value, that means our length of development length, is less than equal to 1.3 into m1 by v divided m1 by v plus L0. Now what is L0, what is m1, what is vu? I am coming through it. So m1 is nothing but our moment, but this is remember one thing, this moment is as alternate bars are bent up at support, so the moment of resistance may be taken as the half of the span moment. So our span moment was how much? Span moment was mu, and mu value was how much? Our mu value comes as 24.54 kilonewton meter. Okay, this is our span moment. But as the alternated bars are bent up in the support, okay, so the moment of resistance we can take as a half of the span moment. So m1 is obviously half of mu, that means 0.5 into mu value is how much? 24.54. Okay, so this one is 12.27 kilonewton meter. So m1 is shorted. Now what is v? V is nothing but our shear force, that is we signify as vu also. So vu is also shorted. Vu is 26.97 as we calculated earlier. Okay, our vu is 26.97 kilonewton, that is our shear force. And there is a new term, that is L0. What is L0? It's nothing but for bend, for 135 degree bend, for 90 degree bend, for 75 degree bend, these values of L0 is different. In case of 90 degree bend, at the support, the reinforcement are in 90 degree bend, so we can say that our L0 is 8 dB, okay, as 90 degree bend from center of support. Okay, so put the values. We can say 1.3 m1 is how much? 12.27 into 10 to the power 6. We convert it from kilonewton meter to newton into millimeter, so that means we have to multiply it by 10 to the power 6 term. And what is our VU? VU is nothing but 26.97 kilonewton. We convert it into newton, so multiply by 10 to the power 3 plus L0. L0 is how much? 8D0. Okay, 8 dB. Sorry, 8 dB. And what is dB? dB is nothing but our dia of main bar. So 8 into dB. dB is 10. So this 10. So this value comes how much? Calculate it. I think you all get this value also. 671 millimeter. And our LD was how much? 404. Right? So we can say obviously LD is less than 1.3 m1 by v0 plus L0, as this value comes as 671. Okay, so this is obviously less than this value. So hence what we assume first, our dB is 10, is satisfactory. Hence design is okay. So you can say by this part, okay, we can solve a simply supported one-way slab. Now let's summarize. First of all, we have to check this is one-way slab or this is a two-way slab. Okay, so by Lx by Ly we can determine this is a one-way or two-way. First of all, we determine this is a one-way slab. Next, move on to step 1. We have to calculate the loads and the effective span value. Next, after calculating the loads and effective span value, from there we calculate our overall depth. From there we calculate our factored load. From the factored load we calculate our effective span. Okay, next to move on to bending, maximum bending moment, maximum shear force. Next we calculate our AST. For determining AST we have to check for the depth for bending moment. So this is the formula for calculating the checking for the depth of bending moment. So by the step by step you can see how easily this problem can be solved. Okay, so that's all for one-way slab. In the next class we will discuss about two-way slab. Okay, so that's all for today now. Thank you.